In this video, we're going to take some time to figure out what affects the solubility of a solute in a solvent. What does that mean? That means that if you have water and you can put sugar or salt in water and it dissolves, what happens to make it dissolve? So that's the key question here. And at the same time, we're going to talk about the rate of dissolution. What are let's see, the concept or the situation that affects how fast a solute or a matter dissolves in another way. So stay put, you're going to see we're going to learn a lot. So what really happens when you try to put a solute, for example, salt or sugar, and you want to dissolve it in water? Here you've got water, you've got a solute that is salt. How is it that something wants to get dissolved in another substance? So here there's an excellent question. The key parts here we call them hydrogen bondings. If you remember well, we talked about molecules in the past, and interestingly enough, some molecules sometimes they are attracted to each other. So let's see. If you think of solvents, a solvent being attracted to a solvent, I'm going to take the example of water. Water is H2O like this, but we do know that we have here an oxygen and two hydrogen. Interestingly enough, because of how it is, and we have valence electrons, we have situation where we have here, where the hydrogens are, the tendency to be more positive, and here the oxygen has a tendency to be slightly negative. So here it's about the electronegativity of these atoms within the molecules. Now, if this one here tends to be more positive, that means that it could attract here another water molecule, where this one is here negative, this one is positive, and this one is positive. So here what we have an example where we have a water molecule here that is attracted to another water molecule, and it is what we call hydrogen bonding. I'm going to give you an example. If you go in the morning and you have the morning dew, or if after the rain, you might notice that you have a blade of grass like this, and on the blade of grass you have, it looks like a little pearl of water like this. And the reason why water would form little beads like this is that you have water molecules that are attracting each other within it, but also creating a surface tension to try to maximize their shape, which is basically a sphere. And you have here what we have a morning dew, and we have these little drops here. Another reason how we can see these, if you have a perfect condition and you have a snowfall, and you can actually see snowflakes, a snowflake like this, The reason why snowflakes are like this is that we have water molecules that are getting close to each other, and they are no longer energized, and they form solid flakes like this based on the attraction between these water molecules and the angles between, so the angle here between the hydrogen atoms here and the oxygen, including the angles with the other electrons that are around the oxygen. But all of this to say that when you have solvents attracting solvents, we have hydrogen bonds being at play here. And interestingly enough, we've talked about these in the past, and we're going to talk about water for the most part because this is the most abundant solvent we have around us. The second force that can happen is If you've enjoyed the video so far, my name is Alain Faber, and I've been teaching science for more than 25 years. I do enjoy learning science and try to share with others. If you've enjoyed this video so far, I'm glad you're here. My name is Alain Faber. I've been teaching science for more than 25 years. I'm answering a question to someone that asked me what is happening with solutions as well as all the other parts related to grade 11 chemistry here in Ontario. So I'm giving you some input. If as we go along, you have any clarification questions, put them in the comments below. I'm always looking at those comments to find ideas for my next videos. On this, let's continue with our learning about what affects the solubility of a solute. Okay. The next force we're going to talk about will be when we have a solvent that attracts solutes. And the example for this one, I'm going to take salt. So if you have salt like this, and it is an ionic compound, what is interesting is that when you put salt in the water, what happens is, as we mentioned earlier, we have hydrogen bonds here. Here, the electronegativity of the water molecules will dissolve the salt, for example, and we'll have some sodium ions, which are positive. And we have, let's see, we have the other one, chlorine ions, that also have here a negative charge. Interestingly enough, the chlorine here that is negative will be attracted to the hydrogen atom here, which is more positively charged, or the electronegativity is positive. And we have sodium that will be attracted to the oxygen, which has a negative electronegativity. So here allows for a solute that is ionic to be able to dissolve nicely in water. And the main reason for that is that we have this idea that there is a polarity within the water molecule, and this polarity allows for these differences in electronegativity within the same molecule. And when you put many of them together, they interact with each other, and then when you put ions, they interact even more. The next part we have here is solute and solute. The reason why the forces get together, so for example, if you have, let's see, I'm going to give an example which will be, okay, if you have pop, for example, you open a can of pop, let's say you use a clear solution, I'm going to say 7-Up, Sprite, or ginger ale, and you put them in a glass, you will notice something that is interesting. You have your glass like this, and you will notice that you might have a little nick in the glass right here, or let's see if we can make it more in focus. We have a little defect in the glass. So what will happen is here you're going to have carbon dioxide molecules that are dissolved here, or not dissolved, but within the liquid here. And what will happen is the carbon dioxide will start to gather, and after a while, they will rise because the density of the bubble is big enough, it will allow it to go up. That is an example of solvent to solute, where similar materials will tend to attract with each other. So that is an example. Another example would be, for example, if you have honey and you have a container of honey, and then you have a little sugar crystal that is opening here, you might notice that after a while, the honey crystals or the sugar crystal would get more and more. And within a few days to a few weeks, we have crystallized honey. And the reason for that is that we have the sugar molecules that will want to attract each other here. And therefore, we have solvent to solvent interaction. So here is the first bit about what happens when you have solubility and why it happens. Let's continue with the next topic. Another word that may come up every so often is the word hydration. So how does that happen in the idea that you have, for example, a solute? Here I'm taking this ion here that is sodium, and because of electronegativity, you have this example where you have sodium and you have water molecule that will be going all around here. And then you're going to say, well, this is like an ion in water. So is it really what hydration is? And that's a good question, because I need to go beyond that. Here we have just an ionic compound in water. But what happens if you have a whole molecule that want to be dissolved in water? So larger molecules like sugar, for example, in which case it doesn't create an ion, either positive or negative. So how is that possible? that you have hydration with those. So let's see if I can show you the example. Another example of how a solute will dissolve in a solvent will be a molecule. Now, if you have a molecule like sucrose, how is that one going to dissolve in water? And here's something interesting we have to keep in mind. If you have sucrose, it's a much larger molecule, so C12H22O11. And here we have a solid. What is interesting with the sucrose is that we have here, so all around the this one, we have OH here, OH here. I think that's pretty good. Oh, there's another one right here. We have on the surrounding, we have a part that is OH. And because we have OH here, what is interesting is that all of those will have a positive electronegativity because the hydrogen here shares an electron with the oxygen, but the oxygen is a much bigger atom. So therefore you end up with here, we don't end up with an ionic compound, but we have here a large molecule, and with this positive electronegativity will be attracted to water molecule. And water molecule, what they will do, they will go around because the oxygen here of the water will be attracted to the uh, the positive electronegativity of this portion here that is OH. And here you have O and water. So what happens is all around that sucrose molecule, we're going to have water molecule that will go all around it. Therefore, we call it hydration. And because we have surrounding this sucrose molecule, these water molecule here will be going around the other water molecule and therefore dissolving this one. So here we have a sucrose molecule because of the arrangement will allow for dissolution. And the other option is indeed if you have a molecule that is polar, because it does exist. So if you have a molecule that is like this, that is on one side is more positive and the other side is more negative, what will happen? We end up with one part that is dissolving in water much more easily. So that's interesting. This is how we can talk about hydration. Another point that is interesting is about the conductivity of a solution, depending if the solute is an ionic compound compared to a molecule. So let's see. If we go with the salt, that's an easy one. If you put salt into water, salt here being an ionic compound, so let's see if I can write here NaCl. This compound here will dissolve, and here you end up with the ions. And because these ions are hydrated, they're surrounded with water, it allows for them to move more easily. So that means that when you have anodes and cathodes, what happens is that you have movement that is possible here. So here for this positive one here, we have the chlorine that will go towards there. And here for the negative side, we have the sodium. If you have movement of ions, movements of charge, you have conductivity. However, if you put sucrose in water, you end up with a large molecule dissolved in water per se. However, adding electricity does not, we don't have any charged ions, and therefore, so sugared water will not conduct electricity because it doesn't have those charges that can move from one part to another. Keeping in mind that if you have a molecular compounds, all the electrons are nicely used between each of the atoms here, therefore not available for conducting electricity. I was looking at a textbook and they shared about how when we have ionic compounds, how some of them can dissolve more than others. So the solubility is different depending on two things. One is the size of the ions, and the other one is the charge of the ion. So here we have at the top little solubility. Can we do this? Yeah. And then here it is the highest solubility. So how does that work? So if you take, for example, magnesium oxide, oxygen here has a charge of 2 negative. It has much higher charge than, for example, chlorine that has a charge of 1. Therefore, here we have so much less solubility because the electrons are kept within the oxygen here. So much less opportunity for electrons to move around and therefore to allow for dissolution. Interestingly enough, we have fluorine. Fluorine is also a small ion, but we know that fluorine is quite aggressive in creating a bond and therefore will attract all the electrons and therefore the solubility is much less. Now this is about the charge. So the higher the charge, so here we have oxygen 3 negative. If we had, for example, I don't know, phosphorus 3 negative, that would be a higher the ion will be more charged, it will be harder to dissolve. Now, given the same halogens here, let's see what we've got. The size does matter in this example. So here, if you have magnesium fluoride, fluorine is a small atom and therefore has little solubility because it is keeping all the electrons here. But as we go down the halogen family, we end up with chlorine, which is a larger ion, bromine, that is a larger ion, and iodine, that is much larger. So what happens is that we have those electrons that are the valence electrons on the outside, and they're much less attracted to the nucleus because they're a bit further away. So the size does affect how soluble is matter. So for example, magnesium oxide here, if I look here, I have 0.006 gram per milliliters. Is that what? No, per 100 milliliter, like this. Whereas if you go here with the magnesium iodine, you end up with, they mention here, 148 grams per 100 milliliters. So what happens here is that depending on the charge and depending on the size, that can affect the solubility. Now, the next aspect here is about the fact that some compounds are more soluble than others. So in the textbook here, they mention about the solubility of common ionic compounds in water, because often in the lab, we use water as solvent. I'm not going to put it here on the board, but I'm going to see if I can find a good source and I'm going to put it in the comments below. That'll be a great way for you to review. I think that'll be great. The next one here that I want to talk about, they mentioned that, let's see, that's good, temperature and solubility. So for that one, most of the time, if you increase the temperature of water, if you have an aqueous solution, the more the water molecules will be moving, and therefore the more solute it will be able to dissolve. So this is the ballpark usually of how it works. Often you have graphs of temperature, solubility versus temperature of water, and let's see if I can add a link to that in the comments below. I don't want to put the graph here. I don't think that I want to do so, but it is an information that is available. Perfect. So the question of why temperature and solubility is important is that nowadays we're talking about how in the atmosphere we have an increase of temperature. We call it the global warming. So that means that if the atmosphere is increasing in temperature, even if it's 0.5 degrees, 1 degrees, and now we're taking more that the overall temperature has increased by close to 1.5 degrees Celsius globally, that means that we have the atmosphere that has molecules that are moving faster, enough to dissolve more of pollutants, more of different particles, and that can affect humans. The other one to keep in mind as well is that if we have a warming atmosphere, we can also have warming oceans, and that's the same thing. If we have warming oceans, that means that we have a change in the solubility of oxygen, for example, in the water, salt, carbon dioxide. So there's a difference in how solubility change. And that's why when we think of environment, it's important to pay attention to possible change in temperature. Very nice, very nice, very nice. Another thing that affects the solubility is what we call pressure. So for example, I don't have a can here, but if you have a pop in a can, for example, and you open the can, you can hear the gas being released from the can. And the reason for that is that if you have a can that is under pressure, that has a content under pressure, you can contain more gas in the liquid. But when you open it, then you have this gas that wants to go away because it's no longer soluble the way it was when it was under pressure. The same thing happened if you take a Perrier water. Same thing. If it is under pressure, what happens is you have more solubility. You decrease the pressure, most of the time the solubility goes away, and we can hear it. Now that can create difficulties. For example, if you know people that are doing scuba diving, the idea of doing scuba diving and going further down in under the ocean, under the water, what happens is that you have the water pressure around your body increasing as you go down. So what happens is that as the pressure increases, the more you can have gas that can be dissolved in our bloodstream. So that means that there's more carbon dioxide, there's more oxygen, but at the same time, you have more nitrogen that gets from the atmosphere, so in the gas tank, into our bloodstream. And there's an increase in nitrogen content in our blood. So that's why if you go down in for depth, you cannot go for a long time, because the longer you stay, the more nitrogen gets into your bloodstream, and our body doesn't need it because it competes with the concentration of oxygen and also the evacuation of carbon dioxide. But in the same way, if you go down, the body can adapt. If you go up back to the surface too fast, the difficulty with that one is that you are releasing the pressure from around your body. So that means that if you have extra gas molecule into your blood system, the bloodstream, then the gas want to get out of the bloodstream. A bit like if you have a can of pop, and then if you release the pressure, the gas expands. So that's why that if you are doing scuba diving for a few hours, and sometimes more, because some people are working underwater, you need to be in a decompression chamber. So they can last a few hours to 24 hours, where they are releasing slowly the pressure, so that as you breathe, the nitrogen gets out of your bloodstream, so that when you are going back to the environment, then you're in a situation where you no longer have extra gas into your bloodstream. And that's why, for example, if you have pilots cannot go do scuba diving and then fly the same day. There's some regulations where if they do scuba diving, there's a time where they have to not fly. There's a no fly time where they need to stay put. Because the reason for that is that if they go up as a pilot in the atmosphere, the air pressure is different in high altitude, and therefore it can affect the gas that is dissolved in our bloodstream, and that can cause problem. So scuba diving is amazing, but we have to keep in mind that pressure does affect how other molecules can dissolve in a liquid. So that is the part that I wanted to say here. And the last bit for section 8.2 here on factors that affect solubility, they're the following. So here they want to talk, how is the rate of dissolution affected when you change some parameters? So let's see what they are. So the last concept of this section is about the rate of dissolving. How does that work? It is how quickly a solute here can dissolve in a solvent. So we've talked in the last bit about how solute can dissolve in a solvent. But the big question is, how can we change that rate? And often, how can we make it happen faster? So the first one is agitation or mixing. So for example, if you are putting, let's see, some sugar in a coffee, for example, you can put the sugar, you can leave it there. If you don't do anything, the sugar often goes on the bottom and it takes a while to dissolve. One way to make the dissolution go faster, we are agitating. So that means you're mixing the solution. By mixing the solution, you're getting the molecules of the solvent to move around faster and therefore making the solute to go in between the solvent molecule. So that's the one. Or you can say mixing is another great way. Another one is about temperature. If you raise the temperature, what happens? The molecules go faster from the solvent side. That means that the solute can dissolve even faster. On the opposite, if you cool down a solution, what happens is that the dissolution will slow down because the water molecule here as a solvent are slowing down and therefore not going faster. I remember when I have in grade 9 when we were talking about the physical properties of matter, one of my question is if you want tea and you want to know how do we get the tea the fastest? Is it in warm water or in cold water? Now, if you have warm water, you put your tea bag and quickly, especially if you're mixing it in hot water, the tea happens quickly. If you're doing it in cold water, what happens? You put your tea bag, and what happens? It will get the flavor going, but much slower. And if you let it go for 5 minutes, it will not even be as strong as if it is with warm water. So here the temperature makes a difference. The other one here is about the surface area. The idea here of surface area, if you take coarse salt and you want to dissolve it in water, it will take more time than if you take fine salt. And the reason for that is that you have more of a surface area. If I make a cube, for example, I have a cube like this, and if it's 1 centimeter cube, this has 6 centimeter square as a surface area. If I was to cut it in half for each of the sides, you have like this, and then I cut it for each of the portion like this, you end up with here 12 centimeter square. So by breaking it down, by increasing the surface area, you can actually change the rate of dissolving. And that's important because sometimes time is a factor. Sometimes you want to have a more uniform solution. Therefore, you need to pay attention to that. Now here it's mostly about water, but keep in mind that if you are taking care of metals, for example, brass or stainless steel, the temperature will make a difference because you want to be able to have the best mix as possible. If you have large chunk of metals, it will take longer to melt and therefore it will take longer to get together and bind to create a new type of materials you're working with. So this is what affects the rate of dissolving. So if you've enjoyed this video so far, please thumbs up. You can subscribe to my channel indeed, and I'm making videos for you to learn chemistry a bit more. So on this, I'm going to put a link here to another video. If you have any comments or clarification questions from this video, don't forget to put it in the comments below because I'm here to help you as much as possible. On this, I'll see you in the next video.